Well, thank you for inviting me to talk at this, the BAA Variable Star Section meeting 2023. My talk, as you can see, has got the catchy title of PCEB variables and a medley of software tools. And the whole point of this is I really want to demonstrate the software tools, a whole suite of software tools that I've developed over the past few years, where I've been working on this subject of post-common envelope binaries, binary variable stars, and the possibilities that they might have exoplanets orbiting around them. I've been working with three other BAA amateurs on this for a few years now, but as I say, I've developed a suite of software tools, and I really want to introduce those to you, as I feel they could be useful to other variable star photometrists, and so it could be quite useful for you to see them. So without further ado, my background is been a keen amateur now for well over 50 years. Been a member of the South Downs Astronomical Society on the south coast near Chichester in West Sussex. Member of the BAA since the early 70s. John Mason, the current Meteor section director, was my earliest inspiration, as was Patrick Moore, as he was to many of us. I was lucky enough to live with just a few miles from him during his life here in Selsey. Eventually I obtained a degree in physics with electronics from the University of London, graduated in 1981, and I've had a varied career as a techie the whole of my life. Working life, a seismologist in Africa, R&D electronics engineering in robotics and medical electronics, and then latterly, or for many years actually, a professional programmer, well trained by the various companies I worked for, working in assembler and upwards into large scale software systems. I retired after selling my company in 2019, and I live in a lovely little place called Ham near Selsey on the south coast. And here is a photo of the house in the distance and my handmade dome in the meadow there. Actually, you're looking to the side of the dome there, to the right hand side. The Isle of Wight would normally be visible across the way there, so the coast is just a mile away from where I've taken this photo. In the dome I have currently a 9.25 inch celestron, all configured for imaging and photometry with a CCD camera and filters and all the usual auto guiding gubbins, etc. So and astrophysics mount there, which I've had for many years. So I'm also lucky enough to, for the last couple of years, I had a really lovely system in pixel skies in southern Spain. Here I have a C11 with a similar sort of photometric and imaging setup, and of course it's very often clear in Spain, and so it's a really lovely place to visit, and the skies are absolutely superb there. So I'm going to be covering the following things in this talk. I'm going to introduce the research so you can see why it is we needed these software tools, and then I won't go through them here, but I'm going to go through the website I've developed and the various tools, and give some demos. So okay, next thing I'm going to do is to introduce the Altair group. So a quick word about the Altair group. As you can see here, it was formed in 2010. I came along in 2019. Two of the original members, David Pulley. David is still the longest running member of the group currently. Sadly, George Fallis died, passed away in 2020. He was a very enthusiastic member and one of the original members. And John Mallet, also from Selsey, he's really responsible for getting me involved. And also John is very keen on the accuracy of our photometry, and he's the one behind the initial photometric work, as I'll talk about later, that we use as our main photometric system. And then there's Sebastian von Harwich. He's a PhD. He keeps us on track with some of the maths and the physics when it comes to writing the papers mainly. So it's a good team. We all have different skills. And as it says, we're interested in the detection of circumbinary objects around these very short period post-common envelope binary stars. And the thing is that the NASA Exoplanet Archive, this is where all of the exoplanets that are discovered by all the different techniques are listed, many thousands of them, but only 12 out of the 5 or more thousand stars are listed as belonging to these kind of systems and have been discovered by the technique called eclipse time variations. So what we do is we monitor the eclipses of these PCEBs and we attempt to determine the times of these minima as accurately as possible. Now that means in our photometry, we're not so much concerned about using photometric filters to get very accurate magnitudes. What we're more concerned about is perhaps getting as much light as possible from some of these 13th, 14th, 15th mag stars. So that we can take images as quickly as possible and get the most accurate curve we can. So we're interested in good time resolution and the shape of the curve rather than the absolute magnitude of the curve. And if we look at this slide, I'm just introducing this because there are two distinct sort of categories of these objects, light curves, and those are due to the type of stars that make up the pairings, the binary systems. If you look at the top right one, this is the more typical smooth curve of a subdwarf, a typical subdwarf with an M dwarf companion. And these tend to have, here you can see, if I just point here you can see the secondary and then the much deeper primary, and we tend to monitor primaries, and we, as I say, we try to get as many samples down this primary so that we can get the most smooth and accurate curve so that we can determine the time of minimum as accurately as we can. And then you come across this kind of square shape. We call them flat bottomed type. This one is R. Kiley that we monitor with telescopes in Australia and in the southern hemisphere certainly. And as you can see, they have very sharp ingress and egress, and it's quite hard actually to get samples on those, and we determine the middle of this eclipse in a different way, as I will describe, a totally different way than this one. And this is because this eclipse here is sharp-sided because these are typically white dwarfs with M dwarf companions, and the white dwarfs are much smaller compared to the M dwarf, and so it's a bit more like a sort of an exoplanet transit, if you like, where you get a very steep side. And so just bear in mind those two shapes of light curves, because I will talk about how we determine those minima later and the software I've written to do that. And I just want to also say that we have published many papers as a group, and the last paper, but one paper was published in the Journal of the BAA in 2020, Eclipse Time Variations and the Continued Search for Companions to Short Period Eclipsing Binary Systems. And the most recent one that we're very proud to have had published in the MNRAS, the monthly notices. This one is entitled Eclipse Time Variations in Post-Common Envelope Binaries. Are they a reliable indicator of circumbinary companions? And the reason why we've gone this way is because as we've continued to measure these systems, we haven't actually discovered any exoplanets ourselves, but what we are continuing to do is to cast doubt on the many predicted, on the models that have been created and used to predict the existence of those circumbinary objects, those exoplanets. Now, we have found that these predicted models do not hold water very long, as I will describe. And we've also written to the NEA, this is the NASA Exoplanet Archive, because even though our paper has cast doubt on this, we still haven't got anything in the entries to say that these exoplanets have been contested. So Now I'm going to move on to the first of the software demos. I'm going to demonstrate the Altair website. So I shan't go through these points on this slide. I'll just move straight on to the demonstration. So I'm now going to demonstrate the Altair website, at least some of it anyway. And here we are. We're in my browser on my computer here, and I've navigated to the website, which is hosted at Altair EBSRG, that's Altair Eclipsing Binary Star Research Group .pythonanywhere.com. Pythonanywhere.com is a hosting service for Python, obviously, Python programs and websites. And this whole thing has good amounts of storage. It's got good performance, and it costs me about £2.50 a month to rent, if you like, the space on their servers. And I think that's a pretty good deal. But anyway, if you were to go to that address, you would be presented with a login page. And of course, only the members of the Altair group or those that we give access to have a login. But you can either log in or you can look at the About page. So anybody coming in looking at this who hasn't got a login can look at the About page. I'll quickly show you that because it does describe in some detail the history of the group. And what the other really useful thing is all of the papers that have been published. There are direct links to them here, so you can go to any of our papers and see what we've been up to. So that's the About page. I'm going to quickly log in to my login here, and here we are. I'm now logged in. I'm in the home page, and every user is presented. Every user who has an account, I know, or the system knows where that person lives, and they also have their own observatory and its location stored. In my case, Ham Observatory. And so there's an almanac presented to you immediately of what's going on in the sky: sunrise, sunset, astronomical twilight, nautical twilight, that kind of thing, moon, etc. So that's a handy little thing. And there's a whole page of video tutorials for the users to help with some of the more complicated parts of the system, including other tools, not just the ones that are on the website. So now back to the home page. So the first main page to show you is obviously the toolbar on the right here. I'm just going to look at the binary stars being studied. So this is a list of the binary stars that we're actually studying. And so if I click on, say, for example, HSO 705, as I showed earlier, it takes me to the page for that star, which gives me a summary of all the various bits of highlight information about the star. And then there are various buttons that I can press. So for example, if I click primary web link and I go into another page, which is the Simbad page for that star, etc. And then I can do all sorts of other things. And one of the main things I would like to know is, say, for this star, for any of the observatories which we have, I'm just going to quickly go into the observatories link and show you. I can add a new observatory, or anybody can add a new observatory. These are the observatories that we currently use and have used in the past. As you can see, there's various iTelescope observatories, Fulks telescopes, and our own personal telescopes. For example, Ham Observatory here for me. So these are the observatories that we've got observations stored for. So I can ask for predictions for any of those observatories on what's going on in any night or whatever. So if I go back to that star again, HSO 705, and I now go to predicted nighttime minima, it's now calculating, and it has calculated for my observatory, which is the Ham Observatory. It's calculated the next few days of eclipse timings for my location. And so for tonight, which it's telling me that in actual fact, local time, there is an eclipse at 0025 at 33.4 degrees, and the moon is quite low, and the moon is 42 degrees away. So the moon's a little bit close, but it's not super bright, 49 degrees, but that's a little bit low, so I would probably go for this one at 2:45 BST, and it's then reached 43 degrees. We try to keep our observations at 40 degrees and above if we can, and then I can look at the observing plan for that, and I will be presented with this graph which shows me the passage of the star, the astronomical darkness period, and the various twilights, and where the moon is, and the sunrise, sunset, and so that's quite handy to know. It also tells me the time of meridian transit, which is always handy if you're trying to avoid a meridian flip in the middle of the observation. So that's very handy. But one of the really, that's how I can look at the observations at any. I could rerun that at any of those observatories. And now if I click on the what's around feature, and in this time I'll choose a distant observatory. I'll choose my C11 in Pixel Skies, and I will click the submit button, and it's now going to, rather than just looking at one star, it's going to look at all of our stars, and it's going to give me any eclipse that's happening tonight basically. And so I can choose, I can see, oh look, there's one here at 0036 local time, 52 degrees. That's excellent. But do I need to take an observation of this star tonight? Maybe we had one only 3 days ago. So to find that out, I can look at latest observation by star. And this will show me in descending order the most recent observation at the top, and it tells us that, oh no, I don't need to observe that star because it was last observed 2 nights ago from Ham Observatory, and the next date that we need an observation is not until the 5th of October. So as you can see, but those that are in green are okay, we're keeping up, but as you can see, CF PEG, for example, needs to be observed because it's meant to be observed every 30 days, and it's been actually 39 days. So I need to now go and find CF PEG, so I could click on it. I could go to predicted nighttime minima, and I could go and look for a likely slot for finding a minimum of CF PEG. So these are the kind of predictive abilities of the website, and so I've shown you that. I've shown you the observatories, and what I haven't yet shown you are the observations. So if I click on observations, this is showing us the last most recent observations, and if I click on, say, NSVS 1425, I click on the view, I can actually drill in and view that particular observation for that star that I took the other night. So this was from Ham, and it was on the 5th of September, and it tells me what camera I was using, what telescope, and all the various information, the filter I was using. It tells me the time of start, the altitude at start, the altitude at the end, a little bit low at the end, but that's the eclipse was probably at just under 40 degrees, so that's fine. And you can see the result, and you can see the reference stars and the comparison stars as well. And so if you click on this, you download a full Excel spreadsheet of the whole data that was uploaded. Okay, so our observations are managed like that, and if I go to a particular star, say this particular one, and I click on observations, then I just see the observations for that star, and there are pages of observations, and I can go back and look at an old observation that was taken back in 2019 with a remote telescope in New Mexico. Okay, so and of course the telescopes have all moved from New Mexico now, but there is just one other feature of the website which is very important, and I almost forgot to demonstrate it, and this is the way we manage the O-C plots for the various stars we're studying. So if I use HW-Ver as an example, and I click into look at the details of HW-Ver, along with the various other buttons, there's one for view O-C plot. Now I'm going to click on there, and what we're seeing is I'll go straight down to the graphs, we're seeing two plots. We keep a linear and a quadratic ephemeris, and we upload, we keep, as you can see, there's various coloured dots for the different historical data, and our data is the most recent stuff here with the bright blue colour. And I mean, you're looking 20,000 cycles of HW-Ver is the best part of 7 years. So you can see we've been collecting HW-Ver data for 6 or so years, and this goes back many decades. So what we do is as I say, we have the parameters for a linear ephemeris and the parameters for a quadratic ephemeris, and the O-C values are calculated on those, and we can change those coefficients if we want to, but we normally put in the latest current ephemeris that is normally accepted by the literature, the current literature out there, and if there is not one, we will calculate the ephemeris on our data and any historical data that we can find. So in this case, HW-Ver, we're looking at the latest sort of published ephemeris, if you like, and all we have to do is add a data point, and that just involves, after we found the minimum value, we take the BJD of that, the barocentric Julian date, and we add that in along with a known uncertainty that we've calculated, so that we can have error bars on the O-C plot, and we just add the point. And of course, if we change the ephemeris, then the shape of the curve changes depending on the parameters. And at any point we can recompute the regression. So there's a Python code that takes all of the data and recomputes it to reduce the residuals as much as possible, and it will actually create slightly different parameters than those in the accepted ephemeris, if you like. So what else can we do? Back to the O-C page, and yes, we can edit the values just in case we made a mistake, or if we want to disable a point because it's obviously in error or something, we can do that, and we can just download the latest data in an Excel spreadsheet so that we can do further study. So for every star that we're studying, we have this, and it just instantly builds up as soon as we add a new observation. So that's O-C. So I think that should give you a fairly good overview of the website. There are other tools. For example, best observatory by star, so you can see which observatory out of a few choice selected ones gives the highest altitude for any of the stars. And there are other tools, ephemeris generators, observatory almanacs, converters for JD to BJD and back, and HJD to JD and HJG to BJD, and all sorts of others that are built in. And I should mention actually that when we upload the data, the system automatically knows the RA and DEC of the star that's being uploaded. It's got JDs in the data going up, and it also knows the longitude and latitude of the observatory that was used. And so the BJDs are automatically generated by the back end of the website when observations are uploaded. So it's all very convenient, and it's all very built in. So okay, I think that gives a fairly good overview of the website, and I'll move on to the other tools. I now want to move on to our photometry tools. We have worked on an automated Python controlled AstroArt solution. So we use the quite popular AstroArt software, which has a really good fine photometry facility built into it. And also, one of the things about AstroArt is that it is in itself scriptable with a VB, a Visual Basic like syntax, programming language if you like. And so you can really automate AstroArt itself with this syntax, this scripting. And then if you like, we've put a wrapper, or I've written a wrapper around that in Python. And so that manages all of the the sort of housekeeping stuff that we need, the consistency of the check stars and the reference stars, and other stuff about selecting the right kind of combination of telescope and camera and all this sort of housekeeping, so that everything is automated. So the Python handles all the housekeeping, and it launches the AstroArt program which runs its script, and it does some quite clever things. So we are very, very keen on high quality, keeping the quality of our photometry very high. So we do a lot of QA, and we do a lot of QA checks to make sure that everything's going well with each image. Within each image, we'll check quite a few things like the roundness of stars and various other things. And we also have a dynamic process to determine for each image the best photometry aperture in the differential photometry process by looking at the best aperture giving the highest signal to noise ratio. So that works very well. So as I said, we make sure we do ensemble photometry. We normally choose 3 reference stars and a check star for any target, 3 to 5 reference stars anyway, and we always want to use the same ones. We very carefully select our reference stars, our comparison stars, and we want to make sure that anybody using this system the system will automatically pick up those stars and use them. So it does all that and produces lots of reports that are very useful for us, lots of graphs of the light curves, and various uploads that are ready for the BAA and the AAVSO databases, and also the upload that we need to upload into our website, as I've already described. So okay, so I'm just going to move on now and do a very quick demo and show you the photometry process actually in action. Okay, so what I've done here is I've run the Python, the Windows application that is the front end for this particular Python photometry process. Now I use the built-in Python Tkinter Windows GUI library and build the Windows dialog boxes from that, and this makes it a lot more convenient to for all the group just to run this program and standardize on everything. So behind this there are a number of standard files that list our the star systems, the details of the stars that we want to work with, and also for every one of those stars the check star and the reference stars with all their details, so that we are very consistent across the team. And also we keep another file with all the possible observatories that we have been working with, and that stores not only the details of whether or not whether the names of the observatory, the telescope, the camera, the longitude and latitude of the observatory. It also stores things like the field of view and the gain and the readout noise and the dark current of the particular camera combination. So if I choose a totally different telescope, for example something like T30 in iTelescope in Australia, I've got a completely different longitude and latitudes, totally different field of view, because it's a different CCD and camera and telescope combination. But for this particular demo I'm going to use my C11 at Pixel Skies in Spain, because that's where this data was taken, and I just need to set up a few settings and then tell the system where the data is located, which is in this particular folder, and there's a bunch of fit files in there. And so once everything's been just selected and set up, after a night where you've taken your images, you just need to set this dialog box up, and I'm just showing you this folder here in my Windows Explorer, my file, and you can see that there's nothing but one file, which is actually just the settings that I've selected that are stored there, and this will fill up with all sorts of files once I run the process. So I'm just going to click and run the process now, and it's going to process, I think, about 30 fit files for this star NSVS 1425, and then at the end of it that folder will be full of output files. So here we go. So you can see it's running AstroArt, passing various parameters and now processing. It's actually calibrating on the fly, plate solving, and doing all the checks that I've talked about, all the various checks on star roundness and whether or not it can see all the reference stars, check stars, lots and lots of checks. And it's actually running a script, which is the scripting language that is built into AstroArt. So that's 18 fits. It takes about a second or so per image if it's got to calibrate. If it's not having to calibrate because, you know, for example, the files we get back from iTelescope, I always choose the pre-calibrated files, and now it's finished. So it normally does that a lot quicker, but in this case it's copied all of the 26 fit files. It's did all the calibration and everything is done, and now I've got a whole load of files in this folder that I can look at. And one of the first things I can look at is the resulting plot, and here is the result of this particular minimum, this primary minimum of this star. As you can see, it's a nice looking smooth curve, and so on and so forth. And there's all sorts of reports telling me whether or not it was good quality. I can check whether or not there was any saturation going on, and then there's also a web report which I can use to upload this to our website. So so that's the whole process. There's a BAA report. There's no AAVSO report in this particular example, and that's because the stars were APAS stars and not AAVSO comparison stars. I sometimes keep two versions of the comparison stars, one for AAVSO and one for non-AAVSO. So anyway, the whole thing has finished and produced the output, and you can have a look at, if I open up just one of them here, let's say frame number 4, it's opening up AstroArt. Here's the calibrated output, and if it has produced a special file which AstroArt understands. So if I drag and drop that file onto here, you will see that AstroArt will show you the full photometry as if you had done it manually. So here we can see the variable, the various reference stars, and the check star. So, and the photometry, you can perform that, and now we've got the magnitudes of the target star. But all of that stuff was done automatically and in a batch mode. Okay, so I think that's the end of the photometry demo. So I'd like to move on now to what happens after the photometry has been run and we produce a light curve, as I just previously demonstrated. As I mentioned this earlier, there are two different sorts of flavors, if you like, of curves. The first one is this kind of curve you can see here, which has got a nice primary with a fairly symmetrical shape. And when you've got a curve like that, which is probably the majority of the stars we study, we use an algorithm, and many it is the staple algorithm for finding the minimum of a curve like this. It was developed by Quee and Van Woerden in 1956, and there's a paper available with their algorithm. Now it is available in the program Peranzo that you have to pay for, and also there is a version in Bob Nelson's excellent Minima program. But we wanted to have more control over this, so I re-implemented the algorithm from scratch in Python, and now I've put a Windows front end on that tool, and I'll demonstrate it briefly in a minute. And it also runs directly from the website. So that's the first flavor of curve. And then the other type we get, like this one from R.R. Kiley, where we have a flat bottom. Well, the actual bottom is, it doesn't matter too much. It is normally fairly flat, but what distinguishes it are the very steep ingress and egress I mean, some of these, like NN Sir, are absolutely vertical. They drop like a stone and come back up very rapidly, several magnitudes in fact. And anyway, the way you can't really get a sensible result out of the Cui-van Woerden algorithm. So what we do is we fit a straight line to the ingress and the egress, and we determine the center of those straight lines, and that gives us a way of finding reliably and repeatably the middle of these curves. There are one or two stars where only the ingress or the egress is steep, and in which case the researchers it becomes that we take the time of either the ingress or the egress, and you have to be careful when you're looking at past papers to make sure how people have in fact determined these minima. But anyway, I'll now briefly demonstrate these tools for you. So here we are in the Altair Cui and Van Woerden tool, which is, I say, this is the Windows version. So it has a Windows front end to the Python code at the back. And the thing you need to do is browse for one of the report files. There are many reports that we produce in the photometry, but this one here, I happen to know is a CSV file which has all of the BJDs and all of the magnitudes in a very simple CSV file, which is exactly what I need for this program. And I select that file, and then if I click, I now need to choose the limits, the left and right limits, as you'll see. So if I click plot data to choose limits, and I'll expand that a little bit. This now shows this is the one that I just did in the photometry demonstration, and all you need to do is to select, let's say I'm going to select that as the left limit, and we normally choose an equal magnitude on the other side, or very close to an equal magnitude, so that one there. And once I've chosen those limits, I can then run the Cui and Van Woerden algorithm by pressing this button. And if I have now a result here, and if I double click that result, it shows you the red line shows you where the BJD was determined as the minimum, and the estimated error in days as well, which comes out, the uncertainty comes out of the KVW algorithm. And another thing I can do, what we tend to do, is I've got a button called bulk run on equal mag, and if I click that, the system will look and find lots of equal mag pairs, and I'll show you one further down. It works its way down the curve, looking at equal mags and running the algorithm again. And then what we tend to do is take three reasonable ones in the curve, and we then have three good examples of the KVW algorithm, and we can then take the averages. I take the averages, and that goes into my clipboard, and I can then use those values to put into the website. So this is a useful tool. You can run as many different algorithms with different curves and different limits as you like. So that's how we determine the minimum of a curve using KVW. And here's the tool that we use for the steep ingress and egress type curve. Similar interface. You just browse for the data file that you wanted to work on, and then you simply press the run button, and out comes a bunch of numbers and results. And then what you can do is to show the plots, and this will show you what the algorithm did. It looked for the steep points, and it made a decision that it was going to put a line between these 2 points and these 2 points, and then it did all the calculations. Now sometimes it chooses points that you perhaps don't like as much as two other points, so there is a feature where you can choose the points and just click on them and manually choose the points where the lines are chosen, but that's fine. And so this is the BJD of the center. And what we also do is that we look at the uncertainties of the magnitudes, and then we put a number in, like maybe 0.05 or something like that, rerun the algorithm, and then that gives us an idea of what the uncertainty of the algorithm is by assuming a certain uncertainty in the actual magnitude values themselves. So that's how we determine those flat bottom curve minima times. So I've really had my allotted time now. My 40 minutes are up, and there are, in conclusion, there are still several more tools that I could demonstrate, and if anybody's interested, they can contact me. But we have tools for data mining, very quickly data mining curves from the AAVSO and the BAA databases. That's a very efficient way of looking at previous data. We have comparison star expert tools that search for likely comparison stars in the various APAS databases, and also has an interface directly to the AAVSO API. We have an FFT analysis tool to look at likely periodic waveforms in the O-C curves, and there are a few others. But what I wanted to get over really was to demonstrate that these tools, working as a team, is and making sure everybody does things in a way that we know how things were done, what comparison stars we use, and all this kind of stuff to coordinate our research. That's the main thrust of these tools, and I shall continue to development. So, well, thank you for watching and listening.